So yes, let's start me with. Let me also extend all of you a warm welcome here to Foursquare and Foursquare Serbia, and it's a special pleasure for me. I was very much part of recruiting the initial team here, and I've been very pleased working with this team and growing it, and we're still growing here in Belgrade. So it's really one of our main development centers. And so it's really exciting to meet the Belgrade tech scene, for all of you to kind of come in here and learn about us and meet us. It's wonderful. I'm Ib Green. I'm a distinguished engineer at Foursquare, and I focus on developing our location, geospatial location data platform, the product that we call Foursquare Studio. And today I'm going to talk to you about a really exciting thing in the geospatial world. And as you can see here, it's the cloud native geospatial revolution. And so there's a bunch of different things we're gonna look at. So let's get going. Let me see here. That's right. Right. So I'm going to just briefly show the agenda. We're going to look at the vision. What is it that the industry is trying to achieve with this cloud native thing? And we're going to talk a little bit about why we're going cloud native. There's 4 pillars of this kind of movement that we are kind of build on each other and come together to create something that's really, really exciting and that opens up new opportunities. So geospatial formats, the new open table formats, cloud native data sets, cloud native tooling. And then we're going to talk a little bit about the opportunities that this gives, both for us as tool makers to better serve people, and for users who want to take advantage of these technologies and maybe the new tools. Going to also discuss some exciting use cases towards the end. So the vision, what has changed, right? It's been geospatial for a long time. Well, the cloud is the big change. And so the vision that we have is really this question: what would the geospatial world look like if we started from scratch and we rebuilt everything from the ground up on the cloud? So, that's really what all of this is about. Cloud native can mean different things, but in this sense, it's about cloud storage. So the cloud storage is a big game changer, and obviously cloud storage is we're talking about things like Amazon S3, Google Cloud Storage, Microsoft Azure Blob Storage. I'm sure there are many solutions out there, but those are probably the most common. And some of the characteristics of this, is that it's an incredible simplicity. Once you put your data on one of these, cloud storage systems, you have serverless access to the storage. You can basically just work with URLs. So it is if you're just accessing files. You don't have to stand up and run a server. Very easy to publish and share data. The scalability is tremendous. We work with certain data sets, public data sets from satellite and so on, that are in petabyte scale, and there's no problem for systems like S3 to handle those. The reliability, S3 and all these systems, they're just extremely reliable, and the cost is notoriously cheap for what we get. So so those are some of the reasons we care about cloud storage, and we want to have solutions that really leverage those things. Now, there are some characteristics of cloud storage if you dig into it a little bit. So what is it optimized for? Well, it works best for very large files instead of tons of little files. And, we talked about the serverless part. But the thing with these very big files is that, what kind of a common theme that you're going to see in many of these geospatial formats is that we take things that used to be stored, all over the place in like a huge directories of thousands, sometimes even millions of little files for tiles and stuff like that, and just turn them into one giant file. And then, you can put like an index into that file. And then once you read that, there's a technology called HTTP range request. So you can you can request an entire resource with an HTTP GET, but if you use an HTTP range request, add some extra headers, and you have a compatible server, and most servers are today. You can actually just request a range of bytes. So we can still read just the pieces that we need from these huge files on cloud storage and still have like a very incremental or fast loading, UI experience, or for an analytics cloud, just load the pieces that we need for a particular analysis. So the cloud native geospatial approach, geospatial data is notoriously big. And it typically has an internal structure. The geospatial aspect of cloud, geospatial data means that things can be grouped together, like columns, that are in a certain location can be, spatially indexed as being, related to each other, near each other, and so on, and chunked in that way. So geospatial data is really an ideal beneficiary of these cloud native techniques. And again, some of the design goals when we design for new formats and solutions for cloud storage is we want data in fewer but bigger files. We leverage these techniques for partial reads from the cloud. We optimize for fewer writes or read-only access to really get the performance to the next level. Now, what this has led to is an explosion over the last 1 or 2 years in the emergence of new geospatial formats that are optimized for the cloud. And this list has grown and it keeps growing, so I'm sure it's incomplete right now. But some of the most important formats that are on our radar here at Foursquare is a format called GeoArrow. It's a columnar binary format. GeoParquet, also another columnar binary format. A flat GeoBuff, it's a row-oriented binary geospatial format. We have PM tiles, where when you work with tile sets, you may be familiar with Mapbox vector tiles or something like that. They're stored in single files. In PM tiles, you store the entire tile set as just one gigantic file. Very easy to work with, kind of copy and move and so on. There's something called COG, or Cloud Optimized GeoTIFF. These are, gigantic raster files with the built-in zoom level hierarchy. There's GeoSAR for multidimensional data for machine learning and stuff like that. COPC is point clouds that have also these characteristics of being, internally tiled. And something we'll come back to a little bit later is to organize these. There's something called STAC, or the Spatial Temporal Asset Catalogs. These are some of the exciting formats that are kind of coming out of this revolution. Sorry, I go a little bit too fast here. So, yeah, probably the most important format for most users is Parquet and its geospatial, kind of sibling GeoParquet. This is a binary columnar format. So basically, these are all about storing tables. And so you can store a table like in a row by row, or you can store it column by column. And by storing it in binary columnar format, you get like a format that you can load that column straight into memory, no serialization kind of necessary. Although in the case of Parquet, it does allow you to encode and then encode it to improve compression and then compress the columns. So this is kind of a binary columnar format that's optimized for on-disk storage. Has a rich type system, which is necessary to kind of be able to capture all kind of tables in binary. And a really important aspect of it is that it has an internal structure where you can see in the image where it's split into row groups. So you can have like 100, 3 gigabyte GeoParquet file, but you don't have to read the entire thing in one go. You can read one row group at a time. And if you have, GeoParquet, which is, I've been personally involved in the standardization and development of, it's basically standard Parquet, but it has metadata to describe which columns are geo columns and which, spatial reference systems do they use and which encodings do they use. And it's focused on what we in the geospatial world call vector geometry, which just means polygons, points, and lines. And so the primary encoding in GeoParquet 1.0 was well-known binary or WKB. In GeoParquet 1.1, more encodings are supported, including what we're going to see on the next page. But it also added a spatial index. It means that on each of these row groups, we can have like the bounding box, metadata with the bounding box of that row group. And so you can scan a GeoParquet file, just read the metadata, figure out which row groups are in there, and then you can check the bounding box of each row group. And then you compare that with the area of interest, the bounding box that you want to kind of examine. If they don't intersect, you don't even have to read that row group. And this, allows many queries to be really, really efficient, because we just load the parts of the GeoParquet file, from cloud storage with these partial reads that we need. So this is getting incredible adoption in the industry. There's a complementary format that is also really exciting, and we've been doing a lot of work on this, and this is called Arrow and GeoArrow. And Apache Arrow is a binary columnar format, but it's not compressed, and it's optimized for in-memory use, which means that the layout of the data on disk is exactly the same as the layout of data in memory. So you can just basically memory map from your network connector this into your CPU memory. There's no serialization, there's no deserialization. I've heard companies that, where big compute clusters were constantly sending data to each other, or spending 70% of their CPU just on serializing and deserializing the data. Well, if they were to switch to Arrow, that just goes down 0. And so that's exciting, but it's also really exciting for us because we do a lot of work on the GPU for our, interactive visualizations. And so indeed, we can not only copy this from disk, move this from disk to CPU memory without any serialization, deserialization. We can actually move it directly up to the GPU and have the GPU work on it without further processing, if we do things in a very careful and exacting way. And so what we do is when we load this compressed GeoParquet or Parquet files, we actually decode them into Arrow and GeoArrow. And so, once they get into the CPU, they and we start working on them. This is the format we work on. And again, it has the corresponding rich type system. Also has something like row group. It's called record batches in this case. It's a great library. It has very strong multi-language bindings. If you're whatever language you're working in, it's a good chance that there is, a library to allow you to work with Arrow, layout, build new tables and lay out them and all that, access them. And, it's zero copy. It's just whenever you can have, and because it's standardized between languages, you can even have a situation where you have, 3 different services in your computer, one, written in maybe in Java, one in C++, and one in Rust or whatever, and they could work on shared memory. They could have a table in Arrow or GeoArrow format in shared memory. They could all access the same memory, and they could all, collaborate, on that data, which I think it's pretty unique. And GeoArrow is just like GeoParquet. It's Arrow with extra metadata to describe geometry columns and stores vector data. All right, so we talked about 2 exciting binary columnar formats, but then binary columnar formats are really great to read from, like if you prepare the data and can write it in that way. Sometimes you need a format, a row-oriented format, so that you can append to it. You can add one row and one row. That's not very easy to do in a binary columnar format, but in a row-oriented format, you can do that. The big traditional format in the geospatial world is GeoJSON. It's basically JSON with a bunch of conventions for how to describe geometries and types like that. But it's very inefficient. It requires a lot of deserialization and serialization. It takes a lot of space, many times larger, 5-10x larger than for instance, Parquet. So flat GeoBuff is a row-oriented format that has many of the benefits, also for vector geometries. It's much faster. And I'm actually going to show you a slide later on that shows you a little bit of the performance differences when loading these things. It also supports spatial indexing. So, if you organize the file. You can also do partial loads. And this also passes very cleanly into GeoArrow. So you can see we can support many of these formats, create loaders, and then we just convert it into GeoArrow without losing any information. And then we can, just work in one format internally in our tools. Now, as we said before, these geospatial formats tend to be very big, colossal, gigabytes, terabytes. And so loading all the data into memory can be a challenge, certainly on the browser and, on a client, just load the time of loading the thing and, hopefully at some point the browser will blow up. But even on a server, right, it can be too big. And so there are different techniques, but a very common technique in the geospatial world is to tile the data. So you create a hierarchy of tiles. And so on the top levels, you have less information, but you can see the entire world. And then as you dig down and you zoom in, you only load the, finer resolution tiles that cover the screen or the area of interest. And then you get much more details. As you keep zooming in, the detail just keep coming and coming and coming, right? So, and this, traditionally tended to be done with things like Mapbox vector tiles. But again, that was a huge hierarchy of files. With PM tiles, we can now, generate all these tiles. We put them into, just one single big archive. So instead of the huge mess of dealing with gigantic directories, we just have a single file, and it's really easy to download and upload and move and do things like that with. It can actually store Mapbox vector tiles. It's one of the supported formats. It can also store image tiles, and it's extensible. So, excited to see what the kind of, new tile formats the community adds to PM tiles. That's definitely a format to keep in mind. When we talk about satellite data, now we're leaving the world of vector data. We're leaving the world of tabular data, and we're now looking at two-dimensional grids of data. And so the format called cloud-optimized GeoTIFF, and obviously this is an evolution of GeoTIFF, which is an evolution of TIFF, and TIFF is a high-resolution, image format. A TIFF can have multiple images, and they can have more than 8 bits per color. You can have deep color, like 12 bits or 16 bits color, which is really good to, capture scientific data. It can have many bands, not just RGB. Some satellites like Landsat and Sentinel, they may have 12 different sensors, one that's, sensitive to sulfur dioxide in the atmosphere or some other pollutant and so on, right? So you can have like 12 bands or something in this data, and, which you can't just do in a JPEG or PNG. But they tend to get very big. They can, a single, GeoTIFF can be hundreds of megabytes. And so when you want to work on them, again, you want to have this, the ability to just load parts of it. And so a COG, a cloud-optimized GeoTIFF, is a GeoTIFF that includes a hierarchy of tiled views for that TIFF. So, many of the similar ideas, but applied to the world of raster. And this one, I want to show you the difference, right? Here we have the same file in GeoJSON, in flat GeoBuff, and in PM tiles. And you can see the PM tiles obviously loads very, very quickly. It's just loads the tiles that it needs. The flat GeoBuff, in this case, it's not spatially indexed. It's binary, so it doesn't have to serialize and deserialize from text the way GeoJSON does, and that loads considerably faster. It comes in here after, let's say, 12 seconds. And then the GeoJSON, 17 seconds, it was still, working on transforming the JSON text into, an internal representation. So not only big size gains by going binary, but also, real performance benefits. Now, as exciting as those formats are, and the many use cases they open, there's another movement that's going on right now that builds on this and really takes it to the next level, and that's open table formats. And so maybe you have heard about Apache Iceberg. There's a project called Apache Hudi, and then Databricks have their Delta Lake. So these are 3 examples of open table formats. And what they do is that they build on cloud native storage formats. And, typically for these, it's Ponquet, and but they add extra capabilities. So if you store a really big data set, like 100 gigabyte, 200 gigabytes, not uncommon for, a geospatial data set that covers a continent or a world, then it's impractical to put it in a 200 gigabyte, per case. What you do is you typically split it up, in this case, in maybe 1 or 2 gigabyte per case, and maybe you have like 100 of those. But you want to work on those as a collective. And so what the open table format does is it allows you to add an additional metadata file on your cloud storage next to your open table formats. And that contains metadata. It contains information about the schema, like what columns do you have, what types do you have, information about which files, that are collectively to be viewed as the rows at the table with the rows and columns. So it basically assembles a bunch of Parquet files and allows you to work on it. And the really nice thing is that this is an open format. So, this description of this metadata file and how to read it and how to interpret it and how to interact with the data is specified. And this means that, multiple query engines that already implement things like, SQL or spatial SQL and, advanced joins and group bys and these kind of operations, they can now adapt and add a backend that works with these open table formats. So more and more query engines are out there. You may have a favorite. We expect to, now be able to read directly from the cloud, query directly, against OK files, on S3 or your favorite cloud storage. And you don't have to copy them. You don't have to ingest them somewhere. They even, with additional file, you don't really want to change the data on cloud, but with an additional log file, you can insert, update, delete, and merge. So the kind of changes you make are updated and then loaded by the query engine and kind of reconciled before it gives you the data back. And it even has transactional safety. If multiple, query engines read, they won't overwrite each other and stuff like that. And it even has, temporal functions. It has like time travel. You can go back in time and see how the table looked at a certain point. Right. So I think I went through some of these, but the advantages of them. I mean, the tool interoperability, I think, is a major advantage. And today, I think many big data using companies have, a case of vendor lock-in. Everyone has chosen like their big warehouse, be it Snowflake, BigQuery, Databricks or whatnot. And it's very hard to get out of that. Now move your data to, open table, store it directly on S3, and now you have the ability to go back to your vendor and have a pretty hard negotiation with them. And you can obviously, it's very cheap compared to a data warehouse. Something like Snowflake is probably a pretty big expense for a company, but cloud storage, as we said, is very, very cheap and it's very reliable. And for me, the most interesting thing is that for people who are a little bit more, technically inclined, for companies that are more technically inclined, you can now simplify your entire data infrastructure. You can take control of your data infrastructure. You can control exactly how your data is stored. You can control, you can switch out query engines and you can build and compose between like a growing suite of tools. So, if you're a data engineer, I think this is something you really should be paying attention to. Right. Now, this was about geospatial. And so do we have geospatial open tables? And the answer is kind of yes. So the big project that's tackling that, it's called Havasu. And so Havasu is a geospatial version of Apache Iceberg. So just like GeoParquet adds geospatial metadata to the GeoParquet metadata, Havasu adds geospatial metadata to the open table metadata. So, if you have a Havasu, a query engine that speaks Havasu, then or understands Havasu metadata, then suddenly you get this extra capability of doing geospatial queries against these. It's It's kind of an open table format. It's developed, by a company, but they're doing it in the public. This company, it's called Werobots. They're building support for Havasu in their commercial version of something called Apache Sedona, which is an open source geospatial query engine. And so it's still fairly limited, but incredibly interesting, I think, technology that we're really monitoring and finding ways to take advantage of. So leaving the world of open table formats, I just wanted to give a brief mention to STAC, the Spatial Temporal Asset Catalog. So when you're working, it started with raster. You needed to, if you look at these satellite data sets, we talked about them, they're petabyte sized. There can be like 1 million images or 10 million images collected by these satellites, Landsat and Sentinel, and they need to be organized into kind of groups. And so the way they're organized is with these STAC, spatial temporal asset catalogs. So they have like a STAC collection that references either other STAC collections or STAC items, and so you can build up a metadata hierarchy. And but this format is increasingly also used to catalog vector data, so it can now organize GeoParquet and other types of spatial temporal assets. So it's good to be aware of. Right. So we talked about geospatial formats. That's really cool. We talked about the open table formats. So cloud native geospatial format, open table formats, but it's all meaningless unless there's data, right? We can obviously start storing our own little data in it. But it turns out that we have a growing availability of some amazing open cloud-native data. I'm just going to mention a few here. So ProtoMaps is a project that's making an open base map of the entire world. And it's obviously a massive amount of tiles, million tiles maybe, to get that all down to resolution Zoom 14 or 15. It's 100 gigabyte PM tiles, and it's being regularly updated. So if you bring in, PM tiles support to your tool, or you find a tool that's PM tiles capable, you should be able to use the ProtoMaps open base map, which is quite beautiful. And maybe the biggest thing that people are talking about is the Overture Foundation. So it's a couple of the big tech companies who come together and trying to pool their resources and build some amazing geospatial data and make it publicly available. And so I believe when I checked last, they had 4 data sets, boundaries, administrative boundaries between countries and counties and so on and so on. They had transportation networks like roads and railroads, and these are worldwide data set. They have a buildings data set that is particularly impressive, and they have point of interest location data. And so at that time, it was 200 gigabytes. Someone, of map data in Parquet, someone told me it's now 500 gigabyte. So they have added, GeoParquet 1.1. They now have spatial indices. I'm hoping they will go towards also adding open table metadata like iceberg and so on. I haven't seen that happen. And then we talked a little bit about like the big, data sets for remote sensing, like including the satellite data. And if you go to Amazon S3 and Microsoft Planetary Computer and those kind of systems, you will find those entire archives, and they're really, truly petabytes of data on the cloud that's publicly available. So these are some example of ProtoMaps here. You can see how it's loading tiles with range requests. You can see the ranges that they're loading from that huge archive here as you zoom in. This is an example of cloud-optimized GeoTIFF. This is one of the big satellite archives that's being loaded incrementally in our product, Foursquare Studio, down here from data from NASA, obviously. Right. So we have formats, we have tables, we have data. What do we do with it? We need tools, right? And so obviously this is exciting, and tool makers are starting to respond. So as we said, a big opportunity here is for anyone building a query engine. And so you would see There's a set of open source databases, very popular, ClickHouse, DuckDB. And so, again, they're, been adding and starting to add support for open table formats and do direct queries against the cloud. No need for you to like copy all this data, ingest it, store it, pay for all the memory and RAM and stuff like that, but just directly, load from query against the cloud. And commercial tools are also starting to add. Databricks has their own, kind of quote unquote open format called, the Delta Lake format. And, others like Snowflake and so on will, increasingly build connectors for open table formats. It's just a movement that can't be stopped. I want to give some special love to DuckDB. So DuckDB is, a new open source database, or new, but it's a database that right now has a tremendous momentum. It's taking, the data science world with storm. It has absolutely blazing performance. It's a top-notch team that's constantly adding new exciting features. And among many other things, one of the things that excites us, that you can be used in many modes, right? So you can use this for ad hoc analysis. You can install DuckDB in your Python notebook, and you can start to do SQL queries in your notebook. And you can do it directly against your cloud native files, right? You don't stand up any database, you don't ingest anything, you just point DuckDB at your data and write your standard SQL queries. It's amazing. You can use it on the front end. They have built a WASM, WebAssembly version of it. So you can bundle it into a web app and actually, run queries up to a certain size in the browser. You can obviously deploy it on your servers, and power queries, bigger queries that way. It can even be done on the infrastructure. You can place it on the infrastructure next to your cloud native data, using some Lambda infrastructure or something like that. And there's a company now, Mother Duck, that also provide DuckDB as a service. It has some really, it's not a geospatial database, but it has some really cool extensions. So it has the HTTPS extension. That's what allow you to query from cloud native. It has an Apache Iceberg extension. So if you have gone through the trouble of kind of adding the open table metadata to your GeoParquet files, now you have the power not to query just a single, GeoParquet, but you can query an entire gigantic table. It has an H3 math extension. H3 is a discrete global grid system. So when you quantize geospatial data, you typically want to use a grid system. We have been much involved in the development of H3, which is hexagonal grids. And so, obviously we're particularly excited about that. And we love that there is an extension for it in DuckDB. And so, yeah, this is a little bit showing how the HTTPS extension works. So you select and you basically just give the file name, instead of the table name here when you do a query. So very easy to use. And let me see. Yeah, and if switching from tables, if you want to create vector tiles, if you have a huge table, but it's too big for you and you want to work with it in tiles, there's a beautiful tool called Tippecanoe. So you can basically feed it a table, maybe in FlatView, BAF, or JSON, or CSV. And it generates one big PM tiles archive. That's easy to use, and you can upload it in tools like Foursquare Studio, or you can maybe ask Foursquare Studio to generate the PM tiles for your, tiled version, and we write the PM tiles for you, and so it's very easy to exchange information and generate it in different ways. You can even install Tippecanoe in your, Python notebook and tile directly from the notebook. So, quick recap: 4 pillars of cloud native: formats, tables, datasets, and tooling. All right, that was a lot. Now, what are the opportunities here? Well, for us, we want to help our users deal with big geospatial data. We're trying to show here global scale data, planetary scale data. And so, obviously, by adopting these tools that are, these formats and these technologies, then, we can allow people to store their gigantic data directly in the cloud. We can store, data in this format directly on the cloud, open it up for other tools, and we can access the data in this way. And so, for someone who is interested in these technologies and maybe making the shift to taking more control of their data stack and so on, would obviously be looking for tools to support this. And this is what we increasingly hear. Another thing that's, it's easy when everything is public. So we talked about a lot of great public data sets, but companies typically, the bigger they get, the more important privacy is, right? They really don't want their data to leak. They don't, may not even be comfortable putting it in a SaaS system. They really want to have it on-prem or really secure. And so, this is where tool vendors can help, making secure cloud authentication, secure networking, like VPN, private link, that kind of thing, offer private compute, single sign-on, and those kind of things. It's an obvious one. And yeah, I mean, again, this is about, as I mentioned, how do we help now the users that want to move to cloud native infrastructure? So, this is a very kind of clean set of technologies. It's easy to understand, but of course, there can be a lot of work involved, and so that's where we can help as well. And by the way, all these screenshots here are from our product, so just cool visualizations on this type of data. Now, we're not just a proprietary company. Our product, Foursquare Studio, is built on very, very strong open source foundations. And so there is an open source version of Foursquare Studio. It's called Kepler GL. We've been building this for a long time, and it's probably the most popular open tool for exploratory geospatial data analysis. It doesn't upload anything to the cloud. You just upload your files there and they stay in your browser. So because of that, it's very popular even with big companies. If you haven't tried Kepler, you can make incredibly beautiful animated map with just a few clicks. If you have interest, I encourage you to look at it. And I even met people here who are contributing and making PRs, and that's wonderful to see. Powering Kepler GL is DeckGL. And so this is something, a kind of a movement I started. This is a framework that uses the GPU in the browser through WebGL, and now we're moving to WebGPU, adding WebGPU support to render millions of points fluidly in the browser. And these are just some example of the type of visualizations you can create when you get the, really get the GPU running. One of the frameworks I worked a lot on is Loaders.gl. So, when we work in the browser, we need to be able to load all these formats into the browser. And so we've created a huge repository of loaders for a variety of geospatial and 3D formats, various type of compression formats and so on. So it's another big project. I think we have almost 1 million downloads a month now. So there's definitely someone out there that's using it. And again, if you're trying to load data into the browser, definitely check it out. This is a little bit of where we are in terms of our support. So Foursquare Studio on one side, which is our proprietary solution, and our open source on the other side. So, a bunch of things are already implemented, some things are in progress. And so, so this is an active, development, and we share a lot with the community through our open source program. We're not only open source, we're under open governance. We are part of the OpenJS Foundation. It's a really big, well-funded foundation under the Linux Foundation. It's, for instance, the foundation that hosts Node.js, which many of you may have used. So we're very proud to be part of that. And we have a subgroup of OpenJS called Open Visualization, where all these frameworks are. And we also welcome, other open source frameworks who would like to go open governance. We love to bring them into this space and provide. We get a lot of support from the OpenJS Foundation. There's a web page, there's a Slack, there's many ways. We have bi-weekly meetings that are open for anyone to join in somewhat Europe-friendly time zone. So I definitely encourage you. I just came from last week. We had our 3rd annual Collaborator Summit. This time we were in London. Microsoft generously hosted us. And this is from the second day, so we had some fall off, but we had over 40 people from a who's who of companies, Geospatial and software companies flying in to be part of this. Beautiful. We had a first day of talking about the frameworks, and the second day talking about all the application developers were showing the incredible applications they were building and sharing their experiences and requests. So, and that's all I had for today. So,
thank you. Are there any questions from the audience? Anyone? Looks like Ib covered it all for you.
Yeah, so thank you very much for the presentation. I have one question. So you have shared with us how you store the data, how you query the data, but question from my side, how you actually process data, like which tools do you use? Is it Spark or something like that? Because like you said that it's a really huge amount of data, but still it's not really clear for me how do you have this fully ETL process for moving from one place to another?
Well, I could interpret that question in two ways, which is either, we're talking about how Foursquare internally processes data, or how do we offer data processing in Foursquare Studio. So, internally we use a variety of tools, certainly including Spark and these kind of things. In Foursquare Studio, we're focused on, at the moment, on Geospatial SQL. And so we're bringing in, we already have a wide variety of connectors. So, we have many customers already chosen a data warehouse. We have connectors for Snowflake, BigQuery, Redshift, Databricks, and so on. So if you have data, it's more than likely that we have a way for you to go in and create this, store credentials securely on our back end, and then our tool will interact with the compute you already have. So, but we're also, working right now, and I can share, we're close to making an announcement. We're working on adding, a lot more, compute capabilities to the tool. So, yeah.
Actually, I have one question, Ib.
Yes.
During the summit in London, we saw a lot of these big companies like Amazon, Google, Microsoft. How are they contributing to the community? In which sense?
Well, from Microsoft, we have the tech lead of DeckGL, and she's obviously she's become a legend, I think, in the open source world because of the support she gives to the community and the quality of of the work and the visualizations. From NVIDIA, we usually have we have representatives who work on their Node.js bindings for CUDA, and he shows us some of the insane things you can do when you make some of these things run on he brings, all of us brings laptops. He brings like a big box like this with a separate power supplies and stuff, right? And he shows like he has hundreds of millions of points that just animate. So that's pretty cool. I think Amazon I just got the news that Amazon had just joined the OpenJS Foundation. So we've been talking to them. They've been monitoring, obviously. They're a customer of us, and you get some of this technology through Foursquare, but we're excited to see if they will start working on this S3, which you could call the leader or the 800-pound gorilla in the geospatial tooling space. They have been investing very heavily in Loaders.gl. They have some formats that they like i3s, which is for massive 3D data, like entire cities or countries in 3D with all the buildings. And they worked very extensively with us and company called Action Engine that's here today, to kind of continue to develop that support. Have been huge investors and sponsors. So those are just some examples.
Great. How does New York Times contribute?
So New York Times has been using these technologies, some of these technologies so New York Times is, I think, famous for the incredible interactive visualizations and the diagrams and so on. And they built some interactive, maybe the possibility to walk through like a New York neighborhood, and then they have an article discussing maybe some issues with the neighborhood or urban decay or whatnot, right? And then, and they, as part of that, they've run into problems and they've contributed fixes for those problems and so on. So, it's been a good experience.
Okay, one question here.
Thanks for the presentation. It was a great overview of where the current state of the geospatial world is. What I'm wondering about, we heard a lot about data formats and storage. On the other side, we have compute. I'm wondering how you see the problem of where we are bottlenecking. Are we bound by compute or storage? And is it that we are trying to find new storage formats to basically overcome the compute bounds that we are already hitting? How do you see that unfolding and where the limitations are?
Yes, so I think that's a really good question, and maybe, one that I haven't given enough the attention that it merits. But I mean, if we look at what we're enabling here, I mean, we're talking about petabyte-sized scale archives and so on. So it's clear that, we're almost, with these cloud-native geospatial techniques, we're almost unbounded in the amount of data we can store. So we're definitely not bound by storage. So, if we're bound by anything, between those two, it would be compute. And, so this need for partial reads, for tiling, for indexing, for making sure we just look at the data that is relevant, that we can apply a bounding box or a time range or whatever, and just load that data so that we can bring down the amount of compute. There's a lot of innovation, going on the compute side that I didn't cover here. We mentioned a little bit with Apache Sedona and those kind of things. So there are things happening, but definitely I would say compute is an answer to that.